Greek scholar. So Pythagoras lived around ancient Greece. I don't know exactly the year, ne? Ancient Greece. And I think he was a teacher and scholar. So he was a teacher and a scholar. And Kiena Olo Wakotaka Pythagorean theorem. Pythagoras Pythagorean theorem. Pythagorean theorem mo etse ba ke?
Yeah.
Okay, so only a right angled triangle, and that's the radius, and this is x and that's y. Then the square of that hypotenuse equals the sum of the squares of the other sides. And what this theorem really means, ne? Go around and let this right angled triangle. Let me just draw it like this, somewhere here. Yes, I think this will fit. Let's say you have a right angled triangle. Okay, I want to make this side a little bit, one side a bit longer, so that it's obvious. So I'll just say, I'll make this 4, or maybe that's too long because the space I have is too short. Yeah. 1, 2, 3, 4. So that's 4 units. And then going up would be 1, 2, 3. Okay. So then this would be 5. 1, 2, 3, 4, 5. Yeah. So what this means, if you take the length of this side, ne? This side is 5 units long, ne? This one is 4 units long, and the other one is 3 units long. All right, so 1, 2, 3. So if I square the length of the blue side, so square means that it moves from being one-dimensional, which is a line, to being two-dimensional, which is a square. Ne? So when I square it, it means this length, 1, becomes 1 by 1. So I have a square there. This length also becomes 1 by 1. And I'm going to do that for all of these, ne? So that can have a square. So the square of 5 get 25. So I must have 25 of these. I must have 25 of these. So that will be 6. 10, 15, 20, 25. So that means that length squared. So it'll be all the way from 1 to 25. The green side would be 16. And the yellow side would be 9. Ne? And okay, level 3, how is square? ke bokae, and ga o ka lebelela 4 ga o square ke bokae, and ga o ka lebelela 5 ga o square ke bokae, ne? So Pythagoras in ancient Greece came up with this theorem. This length, 5 units, square, so then becomes a square. So I can multiply by itself, it becomes 5 times 5, and that gives me an area, which is a 2-dimensional space. And now that 2-dimensional space, it's square. This square, square se, square se. So in other words, if I take 4 and I square it, 3 and I square it means I have 16 plus 9, which is 25. And left 5 I get square impact 25. If I feel a repumule, okay, 8. So then in the same right angled triangle, we use then the trigonometric ratio, sine theta cos theta le tan theta, ne? Sine theta cos theta tan theta. Then I will shumisha these trigonometric ratios. We use them because knowing one of the other will give us either the angle or even the length of the other side. But in any case, the trig ratios, they're defined as follows. Sine is the opposite side over hypotenuse. And now this trigonometric ratio, it refers to this side that is opposite the angle, and then we divide that side length by the hypotenuse. And then we take also the next trigonometric ratio, we take the adjacent, we divide it by the hypotenuse. So that gives us this trigonometric ratio. We take the side adjacent to the angle. And then tangent is defined as opposite over adjacent. Opposite over adjacent. So we'll stick with these definitions for now. And also, we can also write them in a different way. Still the same thing, but on a axis is so. And then we have the y-axis there and the x-axis. So this length here, if this is the radius of a circle, then, and this radius if it at the circumference of the circle, and it intersects at points x, y, then the line that we connect the point where the radius touches the circumference, the x-axis, it refers a height that corresponds to y on the y-axis, and it refers also a coordinate x that corresponds to the horizontal distance between the y-axis and this point here, x, on the x-axis, ne? So if this is the angle formed between the x-axis and the hypotenuse, then we can define the same trig ratio trigonometric ratio using x, y, and r, so that sine theta elegantly y over r, cos theta elegantly x over r, and tan theta elegantly y over x, ne? So that is the long and short of train. I think I should share with you this window. And Iskhali will be joined by Nobu Utlene.
Okay.
Yes. So far yakwagala ke?
Yeah.
Okay. So these definitions, ne, they apply to any triangle, ne? As long as, if let's say you're on an x-axis like this, you can use these ones. And if you're using a right angle triangle, you can use these ones. But they work the same regardless. And even if you write opposite, adjacent, you won't get penalized for using opposite versus adjacent there, or y over r there. You won't get penalized. But what you would get penalized is if ulebeletse this angle, or when I go explain our cos theta, if you shumisha this as adjacent, then you get that wrong, because you're giving sine of that angle, not cos. That's the only thing that could make you score negatively in your test or exam. So Skadi Chaba, these trig ratios, they work the same regardless of whether Ushumisha this notation or that way of writing. But the definitions are the same in any case. And Dirotushali to make sense, I guess, of the triangle over rectangle. And then secondly, in metric, I get the three-dimensional problems. So they start with two-dimensional problems, ne? 2D problems. So a dimension is something that we measure. Something that we can measure. Let's say dimension. So it's a measure of a spatial extent, especially width, height, or length. So, or extent or magnitude or scope. So size or an aspect or element. So something that relates to something. But long story short, a dimension is something we can measure in space. Ne? So dimension it's like something, for lack of a better word, in space that we can measure. That, and it's also the corresponding size, ne? Sizes or magnitudes. Yeah. Okay, so let's start here. Ne? Let's say you are such a small person, you fit on this page, or nada. And then I'm not able to move anyway because all my movement is limited to that space in the dot. So maybe there's 0 dimension. The dot, let's say it's so small, it's infinitely small, but let's say you can see it for argument's sake. And then jiggy jiggy, there's a line. One. Suddenly, it means I can move from there to there and back. But that means I'm only able to move in one dimension. Because I can measure the length that I can travel or move about. But it's only one dimension. Then, let's say for some reason, Pythagoras squares this dimension, and then it becomes an area. Alright? So Pythagoras has squared that dimension. Now it's got one dimension and another dimension, because I'm now able to move this way and that way. So I've got 2 dimensions of movement that I can follow. One, and I can even move this way if I want, or any way. In the block. Né? So this is 2-dimensional space. Now, a 3rd dimension is added if... So an example of where we apply 2D. 2D thinking, like a map. You can't see like a height per se on a map. You can see an indication of what might be a height on the map, but you can't really see it like you see a height map. But, and also Lerena, when you're walking on the floor between point A and point B, if the floor is flat, then you're walking in 2 dimensions because you can go across and sideways. Now, when you jump into a deep swimming pool, or you go underwater in a swimming pool, then you start moving in 3 dimensions. Right? So it means that one dimension so you have that one dimension, okay, and then you also have that 2 dimension that allowed a person to move this way and that way. Ne? That's 2D. Now when you add a 3rd dimension, then you allow a person to also be able to jump somewhere in space, and there's their shadow there. That one. So you allow them to be able to move and jump up and down, or even fly or float, or whatever the case may be. Let's say it's not a pool, but you've just taken like a big piece of space above where they are. That one. So now, in grade 10, we use trig to solve for 2D problems. This is in grade 10. And in grade 12, we revisit the topic and we solve 3D problems. That is why in those exam type questions, you will have a building that's somewhere there. Oh, hey, Nobutle.
Good afternoon, good evening.
How are you?
I'm okay, thank you. How are you?
I am sharp, thanks. I am very sharp.
Okay.
Yes. So,
Afternoon, Musa.
Afternoon.
Evening. Hi, great.
evening. How are you?
Mina.
Yeah.
Get doing, but doing but.
Yeah.
Hey. Yeah, ne?
How did it go on Saturday? Did you guys sort out the incident with the employee who got injured?
Horrible. Horrible. End up having to have an evacuation.
I says.
Yeah.
And then the department people, what was their review?
Luckily enough, they have not issued us with any stoppage.
Oh, okay, that's great.
Yeah, I think it was because we followed the right steps. Just unfortunately, there was an incident that followed that.
Yeah. How much revenue does the company make a day on that plant? You're not sure?
Probably, let's say a month can be 12 mil.
A month?
A month.
Whew.
But almost 30% of that is ESCOM charges. So that's not profits. From sales, 12 mil, and then you start minusing.
I was about to say your overheads must be insane. I mean, it's the power.
Crazy.
And also,
Crazy.
like, yeah, I can just imagine the human capital part as well. From your skills.
Ridiculous, of course.
I can imagine. So,
Yeah.
yikes. Can I share with Musa what's happened? Wait,
Yeah?
were you able to share with Musa what happened on Friday? You were, ne?
I'm not sure.
Musa, were you here when Nogutla was explaining what's happening at work?
No.
Oh, you weren't here. So let me just make it short, ne? Nogutla's company is a mine, and they work with big machines that use a lot of electricity. But if that mine stops working, things like, if let's say the electricity runs out, for example, then things would leak into the environment and they would kill people, plants, and animals nearby. So what I just asked Nobutle now is, how much does that mine make? Because mines make money, right? So how much does that mine make in a day? And in a month, it could be, it's just a guess. It's not official. It's not official. It's just a guess. Could make up to 10 million a month. So there was an incident at work, someone got injured, and then the people from government to inspect these things came, but they didn't stop the work from continuing because the correct procedure was followed. So what we're talking about now is, if there was the situation was different, then they might have been instructed to stop. And that's why I asked the question, how much does it make? Because I wanted to find out how much would they be losing. Yes. Yeah. So, oh, but it's crazy, man. Like, and then what about the person who was injured? When will?
Sorry, man. But we medical treatment case.
Okay.
So that means they're off work. Is that guy okay? Yes. Can he live on and prosper? Yes. After some treatments.
Oh, okay. Yo,
I
I.
know his fate's on his way back. That's how it works. Anyway.
Oh. All right, all right. So, Nobutle, I was just revising some of the basic concepts with Mosane about tricks. So we did talk about them, so I'm just gonna run past like through them kapela, ne? So remember Pythagoras.
Oh, Musa's giving feedback and myself, so I've muted myself.
Okay. Musa? Just mute nyana, ne? Okay, yeah. So I was just we were just revising Lemosane. That trig probably started around ancient Greek in ancient times. And one of the things it was answering was if like to measure triangles, right? And probably specifically triangles with a right angle. So in answering that question, this equation was developed and it's now known as the Pythagorean I guess theorem. And we use that also to define trig ratios using the angle or one of the angles in the right angled triangle that is formed so that we can measure the triangles. But we can also use these trig ratios with some manipulation in other shaped triangles that are not right angled triangles. But we're going to get to that. And then secondly, the trig ratios can be defined for ordinary or freestanding rather right angled triangles or right angled triangles that are in a xy set of axes. And I was just starting with this explanation. Often the word dimension appears, but dimension simply means it's like something in space that can be measured and has corresponding sizes or magnitudes, right? And when we want to when the whole idea of dimensions is thought about, you started at here where there's no movement or ability to move if you're just in one position, which we'll call a dot for now. So we'll say it's so infinitesimally small but visible. So just a dot, and then we place someone who's big enough to fit into that dot. So obviously that person's not going to be able to move, but should you extend a line from that dot into space somewhere and terminate it there, then that person will be able to move in one dimension, left to right, or it could be up and down, depending on how this line is oriented. But should this line be squared, for an example, then it casts then a shadow or projects an area into space. And now that area creates a two-dimensional space. And that two-dimensional space allows that same person to be able to move from dot and across, but now in all sorts of directions. And this you can think about if you're playing sports on a field or you're on a really flat surface and you're just moving about. Maybe your neighborhood and it's surprisingly on a very flat terrain. Then there's this marquee here you're visiting. Then there's the school there. Then there's the pool there. Then there's the shops there. Then the lake. Then back home. But you'll be moving in two dimensions because you'll be able to move from one location to another relative to another point in space. Now, if you take that same one dimension and you cube it, you have a volume, right? You have a volume. And a volume you can think about, like, let's say this is a tank or a swimming pool, or even the area a person may be occupying, like here, plus the vertical height into or above the page, like towards your face. So that would be this towards your face, and this would be flat on the surface there. And this would be towards the person looking's face. So what that allows that little blue person of ours to do is to not only move in 2D space, but to also be able to, if they can leap. If they can fly and hover and move around in 3. And if they can float, do the same, and maybe they'll just be there. Or they just, however it is that they move. Maybe throw a spider web there and then glide across it like it's a zip liner. I don't know. But they'll be able to just be in space and move in 3 dimensions. So now, why is this distinction important? Ne? Remember, Nobuhle, when we were doing trig just recently, we started with like a triangle, maybe that's projected onto a building, and we have to find maybe the angle of inclination or the height of the building or the distance from the building to where the observer is making the observation. So we do those problems. Those are called 2 dimensions because we're looking at a distance across and going above and not into the page. And this is what we get introduced to in grade 10 for how we can use trigonometry. Now in matric, 3D, trig becomes more 3-dimensional. There was a problem we did where there were 2 towers. One was a little bit shorter than the other, and we had to use the information about the one triangle to get then the estimation of the height that cannot be, accounted for, etc. In grade 12, you could get something like that mixed with, oh, by the way, there is another object somewhere and the area between them is a triangle. And now you've got a right-angled triangle on this wall here and another right-angled triangle on this wall here. On this wall here, outside. And now when you have that, you find you have 3-dimensional problems. Let me just shorten that line and put it here, all right? So you find you've got 3-dimensional problems. Why is it 3-dimensional? Because you have a floor, you have a side that's adjacent the floor on one end, and a side that's adjacent the floor on the other end. So think about it as if you are in the room and you're looking at a corner from wherever it is that you're sitting. Let's say you're in the center of the room and you're looking at the corner in the wall where the 2 walls meet, the 2 perpendicular walls meet. They meet at right angle, right? Now, as you're looking at that wall, you can think about the one triangle connecting maybe the top corner and the bottom corner on that wall, and another triangle on the adjacent wall connecting that top corner there. And then you can imagine a line connecting those at the bottom there where the top to bottom lines meet their respective corners on either end. So when you have that, you have a 3-dimension situation. So it's that 2D triangle from grade 10 and another 2D triangle from grade 10. Now they're together in one scenario and it looks like a bunch of triangles all mixed up. And that's what tends to be confusing in a test to exam. But that distinction is important to make so that it's easy to understand how these can be solved. So then, just to solve a couple of, or one problem with the angle of elevation or inclination, for Musa to see, if someone is flying a kite and the string is 17 meters long, and the angle that the string makes with the horizontal is 63 degrees, how do we find the height that the kite is above above the ground, or above where the guy is holding the kite? So if we use sine of theta is opposite over hypotenuse, then maybe we could get the answer. So if we try the 63 degrees and the opposite is h, but the hypotenuse is 17, then the height becomes 17 times sine 63 degrees, and then that gives us that height. So we move from this in our grade 10 work to stuff that's a bit more fun to work with, like and I'll say fun because I'm like that. Fun because they're very fun actually. Where are they? Where are they? There we go. So yeah, in Matric Mosane, Mind the Gap has them. Page 222. 222. And then error rule, sign rule. And then yeah, this is where they come into play. Yes. So you see this image here. And that's showing here. This one here. With the 3 I've highlighted. So that would be the kind of problem that is 3-dimensional that you would get asked in matric. And literally, if you have this side and that angle for this right angled triangle, you can go back to your grade 10 trig and use tan to find, let's say, length of LB, which is why it's 3 marks. And then length of AB, you would maybe use sine rule or cos rule because it's not a right angled triangle, so you wouldn't succeed with just tan or cos or sine. And then if you want to determine the triangle's ABL's area, you'll also use those area rules or whatever. But the point is, this is how these calculations, the trig ratios, develop from between grade 10 and grade 12. But it's the same concept. It's just here you will have to distinguish between what's a right angled triangle where I can apply sine, cos, and tan directly, and what's a non-right angled triangle where I have to use other rules that have the same trig ratios to be able to solve for the triangle. So that's the long and short of it. Then I think from this part we moved to doing some calculator use, and if not calculator use, we also did these types of problems where we revised them rather. Oh, and then there were equations. So an example of equations, oh, my pen is flat. Oof. So an example of equations would be where you have to find the value of, let's say, the angle and correct it to a couple of decimal places. So these ones are literally, again, just solving for theta in this case. But then you use it's on your calculator, and when last I learned it, it was called arc, but you can just write something like this, right? Of, let's say, opposite over hypotenuse, right? If sine theta equals opposite over hypotenuse. And you solve for the other triangles like this as well. So these equations that you see here, and I'll just make one example. Let's say you've got cos alpha equals 0.64. Then this part is literally something like that, not this one exactly. Then alpha would be arc cos of 0.64, and that should give you an angle in degrees. Must be careful not to write angel. Those are something else. I should just finish off these other ones. Theta equals arc cos of adjacent over hypotenuse if cos theta is adjacent over hypotenuse, and also theta equals arctan opposite over adjacent if tan theta is opposite over adjacent. That way it seems more universal. All right, and then so yeah, just to touch on identities again, we started off with the quotient identity. So quotient is the answer you get from division, and this is simply tan theta equals sine theta over cos theta. And then we have now the square identity as well, which is sine squared theta plus cos squared theta equals 1. Ne? We did do some illustrations just to show how they work. But yeah, so I think Nobutle, when we finished, we were somewhere here, but I'll just start here because Musa, we didn't do this with you. I think I only did this with you, Magdalene, eh? This identities, square identity proving and whatnot. Wait, is Magdalene still in the call? Oh, she's muted. Okay. But yeah, so we're gonna do some of these problems. So I'll just start again with this one, right? So there's several types of problems that you can come across where you can use identities. And the first type is simplify. Then there's evaluate. Then there's what? I guess reduce or simplify is reduce. So I'll just put simplify or reduce. And then there is prove. Ne? So with simplify or reduce, reuse, recycle. With simplify or reduce, you are typically asked to break down a complex looking complicated looking trig expression into a simpler rather, or just one trig ratio or expression. Ne? And then with evaluate, you may have to evaluate, ne? So you may have to find the value of something. And 3, with prove, we must show that left hand side equals right hand side, and we can start on either side with any side, right? And I like these prove ones because they really stretch a person's familiarity with maths. But not only that, they're like how comfortable you are manipulating situations to your advantage. And I don't mean manipulation in a toxic way. I mean it in a way that's beneficial. Like
Stop.
Yes. So I just wanna put chargers in because I noticed I haven't plugged in my devices ever since I got here. So they'll run flat. I don't want that. Just give me a couple of moments. So we're gonna do these ones. These ones are simplify. So simplify, it could be, you could be getting a result that's one trig expression, or it could even be a number. Like it's possible that you solve something and the answer you get is 1, and that could be correct. So you don't have to doubt your answer as long as you trust the fact that you did the math correct. Yeah. So yeah. Now that exercise is done, I can go back to my whiteboard, Jamboard. Oh, I guess Magdalene can't see this screen because okay, let me share this one. So I'm gonna share Jamboard because I remember Magdalene still hasn't figured out how to get hasn't been able to, Magdalene's not yet able to view Jamboard without having to view the screen, so I have to accommodate that. Ne? This is today's Jamboard, I believe. Yes, Jamboard.
Otto.
Yeah,
Oh.
I'm still here.
Oh.
I was not supposed to move that frame, but okay. I just wanna. Yes, that's what I wanted to do. Yeah, so I had just finished writing these notes down. So yeah, these are the types of problems you get asked. So I'll just share that. So I guess I'll just I'm looking at the grade 11 Siavula textbook, ne? So Siavula, grade 11, and this is page 250. All right, so if we are to simplify 10 squared theta times cos squared theta. Remember, we know that tan theta equals sine theta over cos theta, and we also know that sine squared theta plus cos squared theta equals 1. So we know this much. That's what we've established. Then when we simplify this, we can say that tan squared equals sine squared theta over cos squared theta. And we also know that cos squared theta, if we make cos squared the subject of the formula there, it'll give us cos squared theta equals 1 minus sine squared theta if we take additive inverses for sine, and we can substitute that here, or maybe we don't need to. Because this gives us sine squared. Yeah, then right there, that's the end. And then another example, let's say we've got 1 divided by cos squared theta minus tan squared theta. So we can say that this equals 1 over cos squared theta minus sine squared theta over cos squared theta. So this is important because we're using these identities and substituting them so that it makes it simpler for us to add or subtract or simplify or whatever, work with this. Ne? And now here, what's happened is we've got the same denominator. So what happens when we have A over B plus C over B, it's the same as A plus C over B. We look for the lowest common multiple. So if we're adding 4 over 5 plus 3 over 4, then the lowest common multiple is either the product of the two, which is 5 times 4, or 20, or if the one is divisible by the other, the largest of the two. So if this were an 8, for an example, then the LC, lowest common multiple, would be 8. But since they're not multiples of each other, it's their product. That gives us the lowest common multiple. So their product is 5 times 4, which is 20. So I'll just write it as 5 times 4 so that we can see that. So when you take 5 and you put it, you ask yourself how many times would 5 go into 20? It goes 4 times, and 4 times 4 is 16. And how many times 4 goes into 20? It's 5 times, and 5 times 3 is 15. And this gives you, I guess, 31 over 20. So likewise, we add fractions like this. Lowest common multiple is cos squared theta. So that goes in once, 1 by 1 is 1. And that goes in there once, 1 times sine squared theta remains sine squared theta. And this, from that, gives us cos squared theta. And we divide that by cos squared theta, and this gives us 1. So that's one way these problems manifest. Another important way that they manifest is the prove way. And when we prove, we pick either side and then we try and work the one side to be the same as the other so we can come to that conclusion. And the most important thing with these problems, is to always mention restrictions. And the first thing we look at with limits is our denominator. So we must observe our denominator and look at it. Then we must ask ourselves, what happens when it's 0? So that denominator must not equal 0. Or there mustn't be any result from the denominator that gives us 0. Because when it does, it gives us that thing that happens when you divide a number by 0 on your calculator. So you don't want that here because we can't even express it in writing because we don't even know how to think about it. Let alone, we're also just trying to pass maths. So, yeah, it's not make sure. So, so if we want to prove 1 minus sine alpha over cos alpha equals cos alpha over 1 plus sine alpha, we want to prove that, then we can take either side. We can start by saying cos alpha must not equal 0 if we're going to take the left hand side. And if we're going to take the right hand side, then 1 plus sine alpha must not equal 0. Because that can happen in either case, in other situations. But you don't want that to happen. So this is our limitation. So we start with our limits, our boundaries, restrictions. Now that we've set our restrictions, we're on to the next. The next step is we've taken the right hand side. Let's say we've taken the right hand side. So cos alpha over 1 plus sine alpha. And we say is equal. Is equal. What can I do to the left hand side or the right hand side to make sure that it's the same as the right hand side? So I'm going to take a guess and multiply it by maybe by 1 minus sine alpha over 1 minus sine alpha. And now it's important to note that 1 minus sine alpha over 1 minus sine alpha equals 1, because this is the same as that. It's the same as having a over a, or 1 over 1, or 2 over 2, or 11 over 11. That's the first thing. Secondly, because we're multiplying by 1, it doesn't change the original statement. It just manipulates it so that it can serve our cause. So now we'll have cos alpha into 1 minus sine alpha over, now I'm going to have at the bottom, at the denominator, 1 plus sine alpha times 1 minus sine alpha. Now there's something in grade 9 or 10 where we multiply things like this, ne? So yeah, so when we do the first one, the answer we get it like this. So it's a times a, and that gives us a squared, and then we go for a times b, and then that gives us, a times negative b, that gives us negative ab, and then we multiply b times a, so that still gives us ab, but the sign is positive this time, so it's plus ab, and then we finally multiply the last b with the negative b, and that gives us minus b squared, right? And these two are additive inverses, so they give us 0, and we're simply left with a squared minus b squared. So we call this difference of two squares, ne? And then the second thing is this one here at the bottom, so I'll just erase it so I can write it where it's bigger. And I'll also erase this one so I write it where it's bigger. Then in the second case, we will have a plus b into a plus b. And this is the same as a plus b squared. And this is not the same as a squared minus b squared or a squared plus b squared. They're not the same thing. All right? So I'll just erase that and we'll start here. So a times a gives us a squared. I just did this multiplication. And then a times b gives us ab. And then we do the same with the second number, which is b times a and b times b. So that would then be plus ab, which is this one, plus b squared. And this one gives us a squared plus 2ab plus b squared. So I'm putting these down so that we can see the difference between having a plus b times a plus b and a plus b times a minus b. So we can see that difference. And this one is important now because of this baby here. And it's important because of that expression there, because we will have cos alpha into 1 minus sine alpha divide by 1 times 1, same maths, 1 times 1 will give us 1. And then we have 1 times negative sine a, which gives us negative sine a. And then we have sine a times 1, which is positive sine a, so plus sine a. And then we multiply lastly the sine a with the negative sine a. This gives us negative sine squared alpha. Have I been saying a this whole time? That's so bad of me. Wow. And then these two are additive inverses to each other, so they amount to 0. And so we are just left with cos alpha times 1 minus sine alpha over 1 minus sine squared alpha. Our square identity is sine squared theta plus cos squared theta equals 1. And if we make cos squared the subject of the formula, then we are left with 1 minus sine squared theta, just as if we make sine squared the subject of the formula, we're left with 1 minus cos squared theta. So we can pick and choose one of the two. The most accurate one is this one. So we'll just substitute that there, and we'll have cos alpha into 1 minus sine alpha over cos squared alpha, and that divides that out, and we are left with 1 minus sine alpha over cos alpha, and that equals right hand side in it. We can also go the other side. We've got 1 minus sine alpha over cos alpha, and we can multiply by 1 plus sine alpha over 1 plus sine. Again, 1 plus sine alpha over 1 plus sine alpha equals 1. So it doesn't change the original statement, but it does allow us to manipulate it into something that can move us in that direction. So we will have 1 minus sine alpha times 1 plus sine alpha over cos alpha into 1 plus sine alpha. So we don't have to cancel these out just yet or divide them each other out, but we can do the same math that we did there. Okay, thank you, pencil. We can do the same math and end up with, in the next step, 1 minus sine squared alpha over cos alpha into 1 plus sine alpha. That equals cos squared alpha over cos alpha into 1 plus sine alpha. We can divide these out, and then we are left with cos alpha over 1 plus sine alpha. That equals our right hand side in it. Does this stuff make sense? I don't think so.
Not to me. I can tell you that for free.
It sounds like just a lot of, yeah. It sounds like how maths looked when I was 5. When I thought of high school maths.
Like, why would we need to calculate 1 plus why?
You know that series, what was it, where the woman was hunting a ex-military guy who used to be abducted by the enemy lines, and then they show her calculating strong. Yeah, it looks, this kind of math looks like that meme.
This maths, maybe
Yeah.
the girls understood it, not the nation.
But long story short, it literally just draws on this, ne? So I want to show you how it then manifests all the way up to, and this is only for our grade 11 work. So it shows up now from this grade, in grade 11, it shows up like this, and then comes back in grade 12 to be part of the exam. Let me just make an example. For an example, Oh, this is the beginning, yeah. Special triangles, reduction. Okay, it's just after. Yes, you see, trigonometric identities. So we've got your quotient identity, which is sine and cos, and your square identity, right? And from that, we can have our they wrote identity. Our department, I thank you. And then, so yeah, they'll show up for like 3 marks in matric, where we just have to simplify stuff. And in some cases, they'd be nasty and they'd fuse it with compound angles like that. So in grade 11, they are nice because it's just us learning how to manipulate the stuff. But the manipulation comes from just identifying that somewhere I can use 1 minus sine to express cos, and somewhere I can use 1 minus cos to express sine. And I'll just end up, you see, like this one is 3 marks because you just have to identify that using square identity, I'll use the numerator, I'll make it sine squared, and the denominator, I'll make it cos squared, and that gives me then tan squared, and that's my quotient identity. So then it ends there. You can't simplify it further. Then you get your 3 marks. All right? But they do show up in matric, but this time, even with compound angles, where you have to now recall that if this trig ratio has 180 minus or 180 plus, which quadrant is it in originally, and does it become negative or positive after I've reduced it? Yeah, one. But yeah, again, in our next lesson, we're gonna go over rather the concept of reduction of compound angles. Yeah, we'll do that in our next class. But for tonight, I think that's all, folks. Are there any questions? Are there any questions? No questions. Magdalene? Mosa?
I have no questions.
No questions. Okay. Yeah, so we can end here tonight, and then I'll see you